next what we will see is that we have till now discussed about the head loss, but how is the head loss related to the energy of the fluid? That may be interesting to us, because in the very beginning of our course, when we were talking about inviscid flows, we were discussing about the Bernoulli's equation, and we found out later that the Bernoulli's equation sort of gives a mechanical energy balance for a system, for a flowing fluid. Now therefore here we are seeing that even we might be tempted in using the Bernoulli's equation, but because of certain losses that may not directly be applicable, there might be certain errors. So these losses must have some relationship with the energy consideration in the pipe flow. So let us look into a bit more details of the energy considerations in pipe flow. The objective will be to figure out that how the head losses are related to the total energy balance. Let us say that you have a pipe of whatever section, say circular pipe as an example, and we are looking for the fluid in the pipe and trying to write an expression for the energy balance. So for any conservation equation we may start with the Reynolds transport theorem. So let us start with the Reynolds transport theorem, where E is the total energy of the system. So we can write dE dt for the system where capital E is the total energy and small e is the energy per unit mass. Okay. So now let us make certain assumptions for simplification, that let us assume that it is a steady situation, so the unsteady terms go away. So when you have this steady situation, the next thing what you do is you try to write this expression for the dE dt of the system, so that it is what it gives the total rate of change of energy of the system. And so if you have a system like this, so of whatever arbitrary configuration, the total energy change of a system is something of fixed mass and identity, and for that the total energy change is given by a particular form of the first law of thermodynamics. So you are having basically some interaction of heat and work. So you have, let us say there is a heat transfer to the system, say delta Q, there is a work done by the system, say delta W. These are positive sign conventions that we will follow. So any heat transfer to the system we consider as positive, any work done by the system, that is energy flowing out of the system because of work, we consider as positive. So let us say that some heat is transferred to the system, and as an example some part of that is used to do work, the remaining will change the energy of the system. So you have delta Q minus delta W is equal to the change in energy of the system. Obviously I am not writing these terms in a very formal way. Whenever in the next semester when you will be studying thermodynamics, you will be studying in details of how to formally write all these terms, but we are just trying to make use of this, and I am just trying to be at your level so that we can proceed further. Now when you write this energy, keep in mind that this energy is the sum total of kinetic energy, potential energy, and anything else other than kinetic and potential energy which is a function of the internal configuration, which we call as internal energy. So let us just symbolically write it: kinetic energy plus potential energy plus internal energy. In books of thermodynamics, internal energy is given symbol of U, as you have noticed maybe earlier, but here because we already use U for velocity, we use just I as a symbol for internal energy to avoid the confusion in the terminologies. Now this equation you can also write as a rate equation. So you can write Q dot minus W dot is equal to dE dt of the system. So this we can write q dot minus w dot, q dot minus w dot of what? Q dot minus w dot for a system, but in the limit as delta t tends to 0 when it is derived, this is same as this for the control volume as well. So this is as good as q dot control volume minus w dot control. What is the control volume? So you have chosen some control volume which is across which some fluid enters in the pipe and it leaves the pipe, and the boundary of the control volume is shown by this dotted line. Now let us concentrate on the right hand side. First of all, this control volume is stationary, so that the relative velocity and the absolute velocity, they are the same. So this will be equal to integral of rho e. So integral of v dot n dA, for the outflow it will be positive and the inflow it will be negative. So we can say that integral of rho u dA for outflow boundary minus integral of rho e u dA for the inflow boundary, right, because we have now lost the vector sense, so we have put the proper algebraic sign to represent the vector sense. Now next is to split different terms based on like what are the important effects. So heat transfer, of course there may be some heat transfer to the system or away from the system. Say you are heating, the wall of the pipe is heated, so there may be a heat transfer from the surrounding to the system. If it is not heated, then also there may be a heat transfer because of the temperature difference between the ambient from outside and the fluid that is there in the pipe, and how such temperature difference may be created we will try to see. Now if you concentrate on the work done. So what is the work done here by the fluid in the control volume? First of all, you have the fluid, let us consider the inflow, the fluid is entering with a pressure P. So it is putting some energy to the control volume as it displaces some fluid and enters it. So what is the corresponding work done? See, we have related this with the flow energy or flow work, so that same work we are referring here. So if you have let us say a small element of area here, say dA, so the elemental work done is P in into dA into the displacement. Here we are writing the rate, so the rate of the displacement, that is the velocity. So P in dA into u, integral of that over the entire area, sign plus or minus. You see this consistency of the first law of thermodynamics. See, any energy in the form of work, if it is transferred from the inside of the system to the outside, it is positive. Here the energy is being put into the system, so that is negative work in terms of the work. So that means you have q dot minus so you have minus integral of P u dA for the in, and for the outflow it will be plus. Okay. So that is the left hand side expression that we are having. Now the next is we are assuming that rho is a constant for this problem or for this discussion. So when rho is a constant, we can take rho out of the integration. In place of E, what we can write? This is energy per unit mass. So first, say if you write first kinetic energy u square by 2, potential energy Gz, and internal energy per unit mass I. Okay. So if you collect all the terms, what you get at the end, So you get q dot Cv. Let us say that you take these terms of integral of p u dA to the right hand side. So if you take these terms to the right hand side, you will see that it will club up with these ones u square by 2 gzi plus that you will have one p by rho, because rho is there as a multiplier. This is just p alone. To adjust with that, you will have one rho multiplier outside. So in the bracket what will enter is p by rho. So you will have this equal to, say if you take rho outside, then integral of p by rho plus u square by 2 plus gz plus I into UdA same thing for the inflow. Now the next important thing is the integration of whatever integral appears in the two inflow and the outflow boundary terms. So when you write this integration, you have to keep one thing in mind, that you have to be careful whether the properties are varying over the cross section or not, because these are integrals over the cross section. So let us assume that the pressure is not substantially varying over the cross section, and that is in a way true, that we have seen that the major pressure gradient is along the x direction. Then u will definitely vary with the cross section, because you have a velocity profile, it is not a uniform flow. The potential energy effect, that also you may consider that the pipe diameter is not so large that there will be a great difference in potential energy effect. So certain terms of these you may very confidently take out of the integral, assuming that those are constants. So like you can for example write say you divide q dot Cv by rho. So one you have p by rho, or let us do one thing, we will divide by rho in the next stage. We will now see that if you take p by rho out of the integral, then what you are left with in the integral is integral of u dA, that is the volume flow rate, that multiplied by the density is the mass flow rate. So we call it m dot. Okay. Next is you have rho by 2 integral of u cube dA. So this is, remember we are writing for the outflow, so let us give some names to these areas, one for the inflow area and two for the outflow area. So this is P1 by rho, this is integral over the section 1, and then similarly this is m dot Gz. If you assume that the temperature is also not varying over the section, then the internal energy you may assume to be a constant over the section, so plus say m dot I. Oh, this is 2, right? Yes. Okay. M dot Gz, this is 2 I2, then minus similar terms for 1. So minus P1 by rho m dot minus rho by 2 integral of u cube dA for the 1 minus m dot Gz1 minus m dot I1. Okay. Now let us say that we neglect this effect, we do not neglect this effect of velocity variation outright, but we somehow make up for our negligence. See, if we do not consider this effect altogether and say that consider that the same velocity, velocity same as the average velocity is there, then one approximation to this term could be half m dot into u average square, because this is what, this is like kinetic energy, because 1 rho into u into dA is like m dot and that into u square is like this one, but this is erroneous. Why this is erroneous? Because this is not exactly same as this one, because m dot is what, rho into u average into A. So u average into u average square is u average cube, that is not same as integral of u cube dA. So that is an error, and that error has to be adjusted with a multiplying factor, say alpha, which we call as kinetic energy correction factor. So this alpha at the section 2, this may be different at different sections because velocity profiles may be different in general over different sections. So this alpha is known as kinetic energy correction factor. So what is this correction factor all about? This is the correction factor to correct the kinetic energy from a hypothetical consideration that it is based on the average velocity to the real kinetic energy that is there integrated over the cross section. So the kinetic energy correction factor will be what? So you have alpha into m dot is rho u average into A into half into u average square, so u average cube is equal to rho by 2 integral of u cube dA. Okay. So you can now write an expression for alpha as integral of u cube dA, this one. Okay. So if it is for a circular pipe, so this is as good as u by u average whole cube, dA is 2 pi r dr by pi r square from 0 to r. So you can calculate the kinetic energy correction factor given the velocity profile. Now can you tell whether it will be more for laminar flow or turbulent flow? Laminar flow. Why it should be more for laminar flow? So it depends on the u by u average, right? So u by u average, it is u deviates from u average significantly more for laminar flow. So you will have a more significant value of this one deviated from 1. So if u was equal to u average throughout, then kinetic energy correction factor would be 1. If it slightly deviates from u average, then it will be very close to 1. But if it is largely deviating from u average, say consider the fully developed laminar flow through a circular pipe. So u center line is 2 into u average. So you can see there is a large difference, and that 2 factor will be there if you consider this kinetic energy correction factor. So it will be a large value. So I will leave it on you as an exercise that you calculate the kinetic energy correction factor for fully developed laminar flow through a circular pipe. Just substitute the velocity profile, that u by u average equal to 2 into 1 minus small r square by capital R square, and then just do the integration. Now you see that this kinetic energy correction factor, if you put, let us see that what equation you will get at the end. So now let us divide all the terms by m dot. Okay. So if you divide all the terms by m dot, you have q dot by m dot is equal to P2 by rho plus say alpha into u2 square by 2, because you have already divided by m dot, which is rho into u bar, then plus g is E2, internal energy term we will just write separately, minus P1 by rho plus alpha U1 square by 2 plus GZ1 plus internal energy 2 minus internal energy 1, right. So, we may just rearrange it a little bit to write that you have P1 by rho plus alpha U1 square by 2 plus GZ1 is equal to P2 by rho plus alpha U2 square by 2 plus GZ2 plus internal energy 2 minus internal energy 1 minus this one, right. Okay. So, many times when you say alpha, maybe it is better to write alpha 1 and alpha 2. Now, if you consider these alphas as 1, this will look like a modified Bernoulli's equation, that here you have the total mechanical energy at 1, here you have the mechanical energy at 2, and you have a term here, the correction term. This correction term, if it is 0, then it is just like the Bernoulli's equation that you have studied earlier. So, sometimes this is known as modified Bernoulli's equation. Again, that is a very wrong concept. This has nothing to do with the Bernoulli's equation except the form, because Bernoulli's equation you are writing between 2 points. Here you are writing the equation between 2 sections 1 and 2. So, be very, very careful. I mean, this is a very important misconception that people have. Many times you see that in some of the industrial applications even the kinetic energy correction factor is omitted, and then still it works. It works beautifully because many of the engineering flows are so turbulent that kinetic energy correction factor is very close to 1. That means considering that or not considering that does not matter, but it is a matter of negligence or understanding. So, if you understand that it has to be there, but for a highly turbulent flow you neglect it, that is one thing, but a very bad thing is you do not know or do not understand that this has to be there. So, that misconception has to be avoided. So, do not take it as a modified Bernoulli's equation, better we just call it as an energy equation which looks like a modified form of Bernoulli's equation with the terms in the Bernoulli's equation adjusted with something. So, what is this now? We will now concentrate on the physical meaning of this. So, internal energy 2 minus internal energy 1, what is this? So, you have basically, let us say that you have, so at the section 2, say at the section 1 the fluid has entered, at the section 2 let us say that heat transfer is 0, let us say that you have insulated the wall of the pipe so that there is no heat transfer across the control volume. So, then what do you expect, that term to be positive or negative? This is pure physical understanding, do not try to go for any mathematics to describe it. Think about this, you have, because of viscous effects, the relative motion between various fluid layers. It is as if like you are rubbing one of your palms with the other. So, you have the frictional resistance between because of relative motion between various fluid layers, and because of that frictional, to overcome that frictional resistance, what will happen? There will be some work that is necessary, but that work is not an useful work. So, the entire work is dissipated, and where it is dissipated? It is dissipated in the form of intermolecular form of energy. So, the fluid gets overheated, so it increases the temperature of the fluid. So, because of viscous action, whatever work is necessary to overcome that, that is eventually manifested in the form of an increased temperature. This is known as viscous dissipation. So, whenever you will be studying maybe heat transfer later on, you will go through the greater details of what is viscous dissipation, but it is very important to have a qualitative understanding of it, that you have velocity gradients between fluid layers and there is a relative motion between the fluid layers. To overcome that resistance, some energy has to be spent or some work needs to be done, but that work is not manifested in the form of useful work. So that what it only does is it increases the temperature of the system through the internal energy rise. So we can conclude that this term is always positive. Now you may say that I will have a heat transfer which is more than this one, but see spontaneously that effect is not going to be there. In a limiting case what may happen, see when the system is overheated you have a higher temperature than the surrounding, so you will have a heat transfer. So this spontaneous heat transfer is what? This spontaneous heat transfer itself is negative. So here you have to remember that this was put with a sign convention that heat transfer to the system is positive. Here the system is getting overheated, so there will be heat transfer from that to the surroundings. So that itself will become negative, so the sum total of that will be positive. That means what you can say is that this represents the total mechanical energy at section 1, this represents the total mechanical energy at section 2, this is a positive term. That means the total mechanical energy at section 2 is less than total mechanical energy at section 1. So there is some loss of energy and that is manifested in the form of the head loss that we have seen. So this expressed in the form of head, that is if you divide all the terms by g, then it is expressed in the form of unit of length or head, that is nothing but the head loss that we have calculated for the pipe flow problems. Now consider one important thing. If we ask you that what is the work done by the fluid to overcome the wall shear stress, the shear stress at the wall, what will be that? Yes, what should be the work done to overcome that? Keep in mind one thing, how do you calculate the work? Some force, or here the rate of work, so some force multiplied with some velocity. So where we are concentrating at the wall? At the wall there is some shear force. What is the velocity of the fluid relative to the wall? 0. That means there is no work done to overcome wall shear stress at the wall. Again this is a very important thing, because these are loose wrong concepts, that because there is wall shear stress there is some work done to overcome wall shear stress and that is why fluid is losing energy and all those blah blah things people give as explanations. But you have to be very particular in this, where is the work if the velocity is 0? So there is no work done to overcome the shear stress at the wall, that work is 0. Only whatever is the work internally that is manifested in the form of this internal energy change, but not a sort of a useful work by the displacement at the wall, obviously because it is a no slip boundary condition. So from this analysis what we understand is that we can cast the energy consideration between two sections 1 and 2 as P1 by rho g plus alpha into E1 square by 2g plus Z1 is equal to P2 by rho g plus alpha 2 into U2 square by 2g, remember all these are average velocities, plus Z2 plus head loss, which is a positive term. This is sometimes known as modified Bernoulli's equation, or better to say this is an energy equation, modified mechanical energy equation, which still represents a conservation but considering a loss. Now what could be these losses? What could be the sources of these losses? One of the sources of the losses is because of the viscous effects that we have already discussed, that is the head loss HF. We could characterize it that how it is different for laminar flows, turbulent flows and so on. But there also could be other types of losses, and other types of losses are possible because of other changes present in a piping system. For example, you have a small pipe. Now that small pipe is getting changed to a larger diameter. Now this is something where there is a loss. Why there is a loss? See, of course the diameter change is there, but why diameter change induces a loss? So if you consider the streamlines like this, the streamlines because of the sudden change in cross section will be having their curvature in this way. So locally what will happen, there will be eddies formed in this way. These eddies do not participate in contributing to the energy of the main flow. So whatever energy is there associated with the rotation of these eddies, that is a loss so far as the main flow transmittal is concerned. So this is also a loss. This loss was not taken into account for calculating the HF. Similar things may be there for, like if you have valves in a piping system, because those are creating some resistances. If you have a valve, so if the valve is totally closed, the fluid cannot flow. If the valve is partially closed and partially open, the fluid may flow. So obviously there may be other forms of resistances, and those losses because of the other forms of resistances are known as minor losses in a piping system. So we will now look into minor losses in a piping system. Again, this minor loss is a misnomer, because sometimes, so when there is something minor, there is something major. So what is this major? Major is this head loss due to the friction, this we call as major loss. But in many practical considerations, minor loss becomes much greater than the major loss. So it is the name major and minor should not be confused in a literal sense. So just because originally the loss considerations were there from the pipe friction considerations, and in one way it is major because in a pipeline if there is nothing else, at least the physical resistance because of fluid friction is there over a length. You may not have a valve, you may not have a sudden change in cross section, but the length of the pipe itself is present. So the reason of naming the major loss is this loss will be there. Other losses, minor losses, are losses, they may be there or may not be there depending on what fittings are there in a piping system. But if they are there, sometimes they are much more important than the major loss. So the relative importance need not be misunderstood. So we will look into some examples for which give rise to the minor losses. So the first example is flow through sudden expansion. So here what is important is we are able to see that there is some loss, and let us say that the diameters of the smaller and the larger pipes are D1 and D2. We are interested to find out the loss because of this flow through sudden expansion, and when we find the loss due to sudden expansion, we isolate the effect of the loss due to the length of the pipe. So we only consider the loss due to this sudden expansion effect, not the length effect. So what we do, we just take a control volume and try to apply the Reynolds transport theorem, momentum conservation. So let us say that we take this section as section A and take this section as section B. So for this control volume, if we want to write the Reynolds transport theorem, so the resultant force along the x direction, if it is x, I am just writing the final simplified form because we have discussed about such problems many times. So we assume it is a steady flow, and VB minus VA, right. Now what are the forces acting on the control volume? So you have a pressure force on the two ends, right. So when you have the pressure force on the two ends, see also there is a shear force here at the wall, but we are neglecting that effect because that effect is already considered in the major loss, okay. So that does not mean that that effect is not there, we are isolating that effect from the minor loss effect. So the pressure force, so what is the pressure distribution at 1? Let us at A. So we have a section 1 which is say far here upstream, and the section say 2 which is at a downstream, and let us consider that the velocity profiles are approximately uniform at 1 and 2. When is it possible? It is possible when it is almost a very highly turbulent flow. So let us assume that the flow is highly turbulent, so that the velocity profiles are almost uniform, that is the kinetic energy correction factor is not important. Now when you have say you want to write the force due to pressure here, see it is important to note that the pressure is acting here in this way, and this is let us assume that this pressure and this pressure is not greatly different, and that will not be greatly different because these kinetic energies are not greatly different, and this length we are not considering so large that there will be a huge loss of head because of the friction. So here you have the pressure at this one roughly same as P1 if P is not located far away from the section A. If it is quite close, then that is possible. So what we are considering is that in addition to the pressure acting over this part, the same pressure also acts over the upper and the lower parts. This is an assumption. So and that assumption is well justified because the change in pressure from this one is not felt so easily by this one, because it is just a small recirculating region. So the change in pressure is felt only when the proper bounding streamlines are making it feel. So here it is just a local recirculation, this does not understand so easily that what would be the change in pressure from this to the subsequent section. So you have P1 into, so the entire pressure here is like P1 and the area is like A2. So that you have to understand this, it is not the area of one but the total area over which as if this P1 is acting. So it is basically P1 into area of the section A, area of the section A and B are the same. So this minus P2 into A2 is equal to rho Q. Now VB and VA, so VB is like V2, that is fine. What about VA? See the velocities here are not contributing to the energy, so VA average is like roughly it is like taken as V1 average. Again it is an approximation. So what it considers is that the average velocity is like this is the part of the section where the velocity effects are important, and this part of the section just has a velocity which is the same as the average velocity as this one, and this is totally distributed uniformly. So that is what is, so there are lots of approximations involved, but many of these approximations are not so bad if the flow is highly turbulent. Now that is number one. Number two is you can write the difference, so practically you are considering this as like section 1 and this as like section 2. Section 1 is this part, this small part. So if you now write the energy equation, like you can write P1 by rho plus V1 average square by 2 is equal to P2 by rho. So kinetic energy correction factor we are not considering because we are assuming it close to 1 plus V2 square by 2 plus head loss. Also the points are so located we are neglecting the change in potential energy. So the head loss we can calculate, so I divide by G to call it a unit of head. Head loss is P1 minus P2 by rho G plus V1 square minus V2 square by 2G. Now P1 minus P2 you can write in place of Q you can write A2 V2, right. So that A2 gets cancelled from the two sides, so you get this as V2 into V2 minus V1. So this is since Q equal to A2 V2, which is same as A1 V1. So that is from this equation. So then you can substitute that HL equal to, in place of P1 minus P2 you will have V2 into V2 minus V1 by so there is a rho here, that there is a rho here, right, rho into this one. So rho gets cancelled out, then plus V1 square minus V2 square by 2g. So if you simplify this, it will be V1 minus V2 whole square by 2g. You can clearly see that, just one step. So what we can get from this one is a very interesting thing, that I mean this shows that this has to be always a positive thing. So the head loss is positive, and it is a function of the difference in the average velocities over the two sections. One special case is that, let us say this is a small pipe entering into a very large reservoir. So you have a small pipe like this, it is entering into a large reservoir. So what is happening is fluid is exiting from the pipe to a reservoir, and then that is a special case of this one with d2 by d1 very large, and then what does it become? This becomes approximately V1 square by 2g. This is known as exit loss. So exit loss is very important in engineering because it signifies the exit of the fluid from a pipeline to a reservoir. So it is a special case where the ratios of these two sizes are grossly different. Otherwise this is the formula straight away you can use. So this is one example of a minor loss. In the next class we will look into some other examples of a minor loss. Let us stop here. Thank you.